I'm going to talk about complexity science from a perspective that's different from what you've heard so far. I'm going to talk about the concept of the maximum information entropy principle and how it can be used as a foundation for constructing complex systems theory. And I'm going to illustrate it with the example that I have been working with for the past decade, which is ecosystems. So I want to start by highlighting something that's been mentioned earlier, and that is that there really are prevalent patterns in ecology. Wherever we look, whether we're looking at insects or trees or birds or even microorganisms in the human gut, we see certain patterns showing up over and over again. I'm going to just very quickly describe some of these. There's the famous species-area relationship. As you census bigger areas, you see more species. But how fast does species richness increase as you increase the sample area? Well, it turns out it increases with area faster than a logarithm of area, but slower than a power law. Why is that? Let's see if we will explain it. We will explain it. If we look at the distribution of abundances of species, let's take a hectare of Amazonian forest, and it might have 100 species of trees. Some of them will have thousands of individuals, and others will be very rare. They may be represented by only 1 or 2 individuals. What is the distribution of abundances across the species? It turns out, if you plot the logarithm of the number of individuals against the rank order of the species, with the most abundant species having rank 1 and the least abundant species have rank whatever the number of species is, you get over and over again from one ecosystem to another a hockey stick curve. It's actually the Fisher log series distribution, and it does a marvelous job describing most species abundance distributions, except, I have to add, in systems that are quite disturbed and changing rapidly, like under succession in the aftermath of fire. If we look at spatial distributions of individuals within species, we see certain patterns. I don't have the time to go into this one in detail, but it shows up over and over again as we look at real data from censusing real ecosystems. If we look at the distribution of body sizes or metabolic rates of individual organisms across all the individuals in the ecosystem, say within the trees or within the insects or within the birds, we see a pattern which is roughly a power law with an exponential tail. And if we look at the distribution of metabolic rates of individuals versus the abundance of the species that the individual is in, we see a relationship on log-log plot with a slope of -1, meaning metabolic rates of individuals are inversely proportional to the abundance of the species the individual is in. There's scatter around some of these patterns, obviously, but these are the general prevailing patterns that show up. There's more. There's a pattern that Neo Martinez showed with the linkage distribution of connecting nodes in a food web. And all of these patterns, including the linkage distributions, I'm going to show you can be explained with the concept of maximum entropy. So the complex systems dilemma that ecologists face, and people in other fields as well, is that there's just a tremendous number of mechanisms. And it's very difficult to know what to choose. If we look at ecosystems, there's predation, mutualism, competition, dispersal, speciation, birth, death, pollination, et cetera, nitrogen uptake strategies, disease resistance, density dependence of population growth rates, sociality, et cetera. With all of these mechanisms, and this is only a partial list, how is the modeler supposed to begin? How do you pick You can't put all of these into a model. We don't have enough knowledge to know how to parameterize them. And so what we do is, if we're interested, if we really like predation, we put that into our model and we ignore a lot of other things. Or we put dispersal in, or climate sensitivity. But all of these potentially could have an influence on those patterns. There's also multiple abiotic factors that influence patterns, variability in the climate, for example. There's stochasticity, historical contingency, the ambiguity of system boundaries. Where do we draw the edge so that we say, we're studying what's inside that system? Ecosystems don't have edges. Everything is connected. There's a difficulty in conducting large-scale controlled experiments. We can do small-scale climate manipulation experiments or removal experiments, but doing them on very large scales is very difficult. There's a difficulty isolating the particular stresses that act on systems. So if we're going to try to predict what the future will look like, we have difficulty knowing how to characterize all of the disturbance mechanisms that are operating. And then finally, ecologists face a very sad problem, which is the increasing degradation and loss of the very objects of our study. It would be like if you were a particle physicist and you had to wake up the next morning worried that the Higgs particle went extinct. They don't have to worry about that. We do, and we see the plots we study, the ecosystems, the species that we focus on, we see them disappearing. All of this makes ecology the study of a complex system. Basing complex systems models and theory on explicit mechanisms and traits chosen in advance often results in arbitrary choices of governing mechanisms, numerous adjustable parameters, and models and theory that are difficult to falsify. Now, I'm not against mechanism, and in fact, what I'm going to show you is that we can get at the driving mechanisms in ecology, but we're going to come at it backwards. We're going to start with a statistical information theoretic-based approach and back out at the end insights into what mechanisms may be particularly important. But we're not going to start by building a model that arbitrarily chooses X, Y, and Z as the driving mechanisms. The maximum information entropy concept, just what the heck is it? What are we maximizing when we maximize information entropy? Well, first, what is information entropy? It's defined by Shannon. I'm not sure if there's a pointer on this. It was defined by Shannon in the 40s. Information entropy is that familiar expression, the sum over n of P of n log P of n. And it's a measure of the lack of structure or detail in a probability distribution that describes your state of knowledge of a system. When we're maximizing information entropy, we're finding the smoothest possible probability distribution that is compatible with what we call the constraints that arise from your prior knowledge. So you start out, when you do science, you always start out knowing certain things, and you want to extend that knowledge, predicting new probability distributions or improving existing ones. So if you use your prior knowledge as a constraint and maximize information entropy as so defined, you end up with something interesting. You end up with the smoothest possible distribution that is compatible with all of your prior knowledge. Now, the method of Lagrange multipliers is the mathematical tool, but we won't go into that. That's how you do the maximization. And basically, it's illustrated here. Here are two functions. Let's suppose we know two things about a system. We know the mean and the variance. And let's suppose both of these distributions have the same mean and variance as what you know to be true, because you had measured it. If that's the case, which one would you pick? You should pick this one. You should prefer the one with the higher information entropy because it makes fewer implicit, unwarranted assumptions. There is if this and this are compatible with all your knowledge, you don't want to pick this one because it's implicitly making some assumptions about other things that you don't have any reason to believe. So maximizing information entropy picks the smoothest possible distribution that's compatible with prior knowledge. It was all worked out by Ed Jaynes, a physicist in the 80s, and this is the method we're going to use. The basic idea, if we want to sort of look at the architecture of this approach to theory, what we're doing is we're going to start with some insight or information at the macro scale and infer distributions that describe the micro scale. So at the macro scale, we have what we call state variables. In thermodynamics, these would be the pressure and the volume and the temperature, let's say, of a cylinder of gas. And knowing those state variables, thermodynamics allows you to predict the distribution of molecular velocities in that container of gas. So what we're going to do is start out with some state variables, which we have measurements for in ecology, and derive probability distributions. And here are the kinds of things you could use this for. Abundances of species. Speakers of languages. If your state variables describe how many languages there are and how many people altogether are speaking them. 7.2 billion people speak 6,000 languages on Earth. What's the distribution of speakers across languages? Incomes of people, sizes of organisms, spatial distribution, speeds of molecules, linkages per node in food webs, occupancy in a spatial grid, et cetera, et cetera. That's the basic structure. There have been many applications of MaxEnt since Jaynes' early work, improving image resolution in medicine and forensics, inferring gaps in economic data, such as input-output tables, deriving the laws of stat-mech and thermodynamics, that was Jaynes' contribution, improving estimation of climate envelopes for species, in other words, predicting distributions of how distributions of species are influenced by the climate parameters in ranges where they are found, predicting linkage distributions across nodes and networks. These are some of the past applications. And the goal of the maximum entropy theory of ecology, or MEET for short, which I'm going to very quickly summarize, is to predict the shape of static and dynamic microscale patterns in ecology. All those patterns I showed you on the second slide, species area relationships, abundance distributions, metabolic rate distributions, we're going to predict the shapes of those. And we're going to do it with one theory across all the taxa that we study, plants, arthropods, birds, microorganisms, across spatial scales, from small patches to large biomes, across habitats. We don't want different theories for different habitats. And we're going to do it with no adjustable parameters and without prejudging what the specific mechanisms are that drive the system. So it's a tall order. And I'm going to, with limited time, you have to go through this very quickly. The basic idea is we're going to show you just one model of this theory, one model realization called the ASNI model, because the state variables in this model are area, S for number of species, N for the total number of individuals, and E for the total metabolic throughput. And a diagram of what the theory is doing is it's allocating metabolism to individuals, individuals to species. We can extend this model, allocate species to genera, genera to families, and so forth, and work our way up a taxonomic tree. And we'll get to that very briefly later. So this, you're not going to be able to, I'm not going to be able to go through this with you in any detail, but MaxEnt gives the shape of two core functions that are the core of the theory: a spatial distribution function, pi, and what we call the ecological structure function, which is a function, it's a probability distribution. It's a joint distribution on abundance and metabolism, and it's conditional on the state variables S, N, and E. And from those direct outcomes of MaxEnt flow all the metrics, all the probability distributions that describe all of those, plus more. So we can, in principle, now test. And we've done numerous tests. We've looked at about 25 distinct habitats. We've looked altogether at over 100,000 species and over a billion individuals. Here's a list of some of the habitats that we've tested theory with, and there are some pictures of them. I'm going to just show you a few tests. I have dozens of slides of tests, but this is observed abundance versus the MaxEnt theory predicted abundance. It's a data dump type test done by Ethan White and his collaborators. They looked at almost 16,000 communities of plants, mammals, arthropods, and birds. So it's a huge data set. Each community has many, many species and individuals in it. And you can see the observed versus predicted abundance distribution from the theory matches up very nicely. Zhou et al. Did a test of the metabolic distribution prediction, and except for a deviation, which if you ask me about it, I think I can tell you why it might be there. At the very upper end, it also does a very good job predicting the theory, predicting the behavior. The most surprising prediction of the theory, and the one which, when we saw it, we said, oh crap, the theory's dead. It can't possibly look this way. Nature can't possibly look this way. Let me tell you what the prediction was. Traditionally, people plot species area relationships by plotting the logarithm of the number of observed species versus the log of the area within which they were observed. And you get a curve. Sometimes the curve is very slight and people think it's a power law. It isn't, but it can resemble one a little bit. You get a curve. If you took lots and lots of species area relationships and plotted them all on the same graph, you would fill space with data points. There is no rhyme nor reason, no coherence in a log-log plot of species versus area. The maximum entropy theory of ecology predicts that if I take all those species area relationships and replot them in such a way that I'll describe, everything should fall neatly on a simple line. It's called scale collapse, and I want to show you very quickly operationally what it is. At any point on that curve, I can define a tangent, z of a. That's the slope on the log-log plot. At that same value of area, that data set had a certain number of species and a certain number of individuals. The MaxEnt theory told us if we plot the slope z of a against the log of the abundance at that area a, n of a, divided by s of a, so we're replotting tangent versus number of species, and instead of area, n of a divided by s of a. What the theory says is all data from all species area relationships should all fall on this solid line. And when we predicted that, we graphed it up, we said it's inconceivable that nature behaves this way. And when we took all the data we could from, in 2008, we took all the available species area data we could get our hands on, about 30 different data sets, plotted up all the tangents on this axis and log of n over s on that axis, and all the data fall nicely around the predicted line. Many people claim that species area relationships can be well approximated by a power law with a slope of a quarter. If that were the case, all of these data points would lie on that dashed line. The power law, nobody in their right mind should ever again say species-area relationships are power law. They're just not. And yet that idea persists. Okay, we can extend the theory. And how much time? Oh. We can extend the theory, add new state variables like genera, or add another resource. When we do that, we get new predictions that are interesting. And in particular, when we add genera, we do something, we alter what's called the size abundance or metabolism abundance relationship, and it looks more and more realistic as we add more and more higher taxonomic levels. When we add more resources, we change the abundance distribution prediction and usually make it worse. So what happens is when you add a second or a third resource, you predict more and more very rare species. It looks like nature is consistent with one resource, namely energy. Of course, we call it energy. It could be water. It could be nitrogen. It could be anything. I want to make just two slides about general comments. I've sort of put all my philosophy off for the end. Complex systems versus what I call hypercomplex systems. Complex systems, in the sense that we can apply MaxEnt theory and learn from it what's going on, are systems that can be decomposed into a macro and a micro level, or perhaps 3 levels, but let's stick with 2 for simplicity. In thermodynamics, we have bulk properties such as pressure and volume, and then we have microscale properties like the kinetic energies of the molecules. In economics, we have firms, nations, total wealth, or GNP, and then we have individual incomes at the micro level. Linguistics, we have the total number of languages and the total population versus the numbers of speakers of each language. That would be a micro property. In ecology, we have bulk properties such as species richness, total abundance, total metabolic throughput of the system, and then we have all these micro distributions that I've talked a little bit about with you. These are the types of systems for which MaxEnt has a natural application. If your system breaks down into this macro-micro pattern, you can use MaxEnt. However, there are lots of interesting systems, and turbulence is the best example of what I call a hypercomplex system, because you can't make a macro-micro distinction in turbulence. Turbulent phenomena occur across all scales, across a continuum. There isn't a natural discontinuity in turbulent media. And so this would be an example of a system where we couldn't apply MaxEnt. At least right now, we don't know how to do it. We've organized a workshop at the Santa Fe Institute in the spring to talk about whether there might be a way to do it. But at least for now, it looks pretty, oops. Uh-oh. I'm not sure
Can we
what.
use the last minute or 2 for questions?
Okay, yeah, I think I showed my last slide, but I'm not sure. Anyway, because this went blank. Okay.
So while we're switching computers, we have time for a few questions. Where's the microphone? And so Sharon will just come over 1 second. Great, though.
Yeah, there was wait just 1 sec.
So regarding the complex versus hypercomplex, is it the discretization that is important, or the number of relationships, do you think?
No, the number of relationships can be virtually unlimited.
So as long as you can have,
it's the fact that there are things you want to know about, which are the micro distributions, the distributions of incomes across people, or speakers across languages, or individuals across species. And there can be arbitrary many of those things you want to understand at the micro scale. And at the macro scale, there are the coarse-grained things that we know how to, we can go out and measure them. Right. And the question is, do the coarse-grained information through the MaxEnt principle, determine the microscale distributions. And it turns out in ecology they do.
But I was asking about the complexity, hypercomplexity, and the question of levels.
Okay.
The effective continuum is that you said 2, and it could be more than 2, so
that's
you
a
left
great
that
question.
open. Yeah.
I'm hoping at the Santa Fe workshop we'll maybe be able to answer that. Right now, I don't know the answer. I suspect that if there's a discrete number and you have enough computer power to run the MaxEnt agenda down the hierarchy, you could do it.
Have a machine learning.
Yeah, exactly. But maybe we'll know the answer later.
Great. Thank you again.
Okay.